The recording has started, and I would request all students to post in their attendance for this lecture as well in the chat box once again. Though we are using the same link, the recording of the attendance happens only when the recording button starts. So you will have to once again post in your attendance. Okay, thank you for that. And let us start with where we had stopped in the morning. I gave you various aspects of and as to how you looked into, say, the various observations one can make as far as a particular data is concerned. And that is basically the main difference between an individual who is just watching, a layman who is just watching figures, and a student of a particular subject who would be making sense out of those figures. Now, when we speak about the complete surface of this planet as such, the Earth, that is, we need to understand, and we've seen it earlier as well, that land occurs or happens to be 29.2%, and oceans happen to be making around 70.8% as such. Obviously, there would be a minor change in point percentages wherever and whenever there is going to be either a rise in the sea level due to climate change, or it's going to be a fall in the sea level due to climate change. When we speak about land particularly, you'll see that nearly 10% of it is continental mountains, and around 19% of it is around continental platforms. Okay, and what is interesting is this part. As I said, that the amount available as land or as ocean will be dependent on the sea level. This part is going to be affected when we would be experiencing a rise or a fall in the sea level as far as responses to climate change are concerned. Here we have to remember that it's not the absolute 11.4% which may come out or which may go under. It is, what I want to make a point at is that it is this 11.4% that would make a difference of a few percentage points here and there. If that means if there is a sea level rise, then of course you would have these regions going underwater. And if there is a fall in the sea level, then of course this would be emerging out as land surfaces as such. Okay, as far as the rest of the parts are concerned, okay, in fact, as you start moving from land into, say, along the coastline into the waters as such, the first thing that you would encounter is the continental shelf, and then you're going to have a continental slope. Then you have continental rises, which make around 4% of it. Another 4% is the volcanic islands, arcs, trenches, submarine volcanoes, etc. The largest two sections of this planet comprise of the ocean ridges, and you will have the ocean basins. Okay, you'll see that if you put them together, 50% of this planet is made up of ocean floors and oceanic ridges as such. 30, nearly 30 plus 22 is 52%. More than 50% of it accounts to that as such. Okay, so these are a few further interesting facts that we need to understand. And let us now delve more into, or making more sense out of the relief that you would say as far as continental shelf and slope is concerned. Now, first thing you have to remember here is this diagram that you see in front of you. It is basically a diagram which is drawn out of geographic liberty, I would rather say. Now, what do I mean by geographic liberty? If you see, the y-axis here is, say, minus 1, 2, 3, 4, 5 kilometers. However, the x-axis, you'll see that within this span, you are fitting in 100 kilometers. What that means is that you are working on, we teach this as a part of map reading and map scaling as far as geography is concerned. This is called as exaggeration. Okay, how exaggerated the profile looks as far as scaling is concerned. Okay, so you'll see that this exaggeration is what, if this is equivalent to, it's nearly 100, 50 to 100 times as such. Okay, and if I am to actually put this to scale, if I am to actually put this to scale, this would look something like this. Okay, this part. Okay, this is the 5 kilometers that we were referring to, and you put that 5 kilometers on this scale. This is how the topography would actually look like for a long distance. So when you are entering into the sea, this is how gradually it may drop further as such. But as I said, we, for academic purposes, we don't normally tend to use this diagram, and this diagram gets divided into many parts. And of course, this is a sketch diagram. We'll have some three dimension. This is a two-dimensional diagram. We'll have a few three-dimensional diagrams as well. Okay, so as I said that this is the continental shelf and this is the continental slope. Continental slope is here. Okay, continental shelf moves into continental slope, and then you move into the margins, and then you go into the deep ocean floors, which extends a minimum of 1,000 kilometers from the present sea line as such. But as I said, that if this is the present mean sea level, okay, the rise in this, okay, let us say even by a few centimeters, will encompass a single significant amount of land under it, and of course a fall in it will open up uh, some areas as well. Okay, and if you can see at this scale, this exaggerated scale, it is throwing open or it is drowning significant amount of land. You can just imagine that the original scale matching the x and y, how much of land would be either drowned or put open in case of a minor, say, change in the mean sea level, or even if it happens to be a few centimeters plus or minus. This is more a diagrammatic, let us say, picture. Okay, certainly not to the scale as such, but you'll see that what we can match here is the depths, okay, till to around 200 meters, minus 200 meters. You're going to have continental shelf. Then you have the continental slope where the slope drops from 2,000 to 3,000 meters. And then you have the continental rise. You call this as continental rise basically because you are moving towards the land from this side, and that's why it's referred to as the rise. It's between 3,000 meters to 4,000 meters as such. 4,000 to 6,000 meter is abyssal plain, which makes up major areas as far as the ocean basins are concerned. Trenches, okay, if you remember, we spoke about them, that they are where two plates are sliding past into each other as such. Okay, such marginal areas of such plates are called are seen as ocean trenches, which are very deep, an average of around 10,000 meters as such. Then you could have something like a volcanic island in the form of, let us say, the Hawaiian Islands are volcanic. The Andaman and the Nicobar Islands near to India are volcanic as such. On the other hand, Lakshadweep Islands, however, let me tell you, are coral islands and not volcanic islands as such. And then this is a common feature that you will find, though it may not in every ocean be called as the mid-oceanic. It's more so in the Atlantic Ocean. As far as the Indian and the Pacific is concerned, it does not run through the centers of these respective oceans as well. But then such ridges are there where, of course, we know that here is where the plates are moving away from each other. Okay, so these are the major features of the ocean floor. And when I was speaking about the ridges as such, this is the ridge. Okay, this is the mid-oceanic ridge, significantly centrally placed as far as the Atlantic Ocean is concerned. But as far as the Indian Ocean is concerned, you will see that it is not as centrally placed as otherwise, nor is it so as far as the um, Pacific Ocean is concerned. In fact, you'll see that it's more towards the Eastern Pacific, and that's why it's called as the Eastern Pacific Rise also. And further south, you have the Pacific Antarctic Ridge as well. Okay. Uh, as far as the Indian plate is concerned, Indian Ocean is concerned, you have some reference so that you can say that it's called as the mid-Indian ridge as well, not exactly towards the center, but that is how things are placed as far as the oceanic ridge systems are concerned. Putting it in another perspective, you'll see this is how a cross section actually of the Atlantic Ocean would look like. And while I was referring to the term vertical exaggeration, how do you measure VI? VI does not mean Vodafone Idea. It means vertical exaggeration. E, this is the horizontal scale upon the vertical scale. What is the horizontal scale? Let us say it is 50 kilometers per centimeter. And let us say it is 5 kilometers per centimeter vertically as such. So if you put out this ratio, it's around 10x or 10 times is what the exaggeration is. Now in the same scale, if we bring in this scale here, okay, let us say it is 5 is to 50. Okay, so the vertical is the horizontal scale is 50. No, it's more than that, I suppose. Yeah, let us say it is 50 kilometers, and the vertical scale was 5, so this is 10 times. So even that scale is 10 times. This is also 10 times as such, and that's why, in fact, we can see these mounds, and particularly the sea mounds as such. If you put it to the right scale, they would hardly be seen as minor undulations on a plane line as such. Okay, what we need to understand is you have to start with the continental shelf, and then you have the slope. A steeper continuation of the continental slope is called as the continental rise, and then you have the abyssal plain. Okay, the average depth of the abyssal plain is 4 kilometers. As such, you may have mid-oceanic ridges and you have sea mounds. And as we also spoke about the fact that we tend to have an oceanic trench also. Here, this plate may be moving down, okay, down all the way here. Okay, so these areas will also be known for earthquakes as such. An interesting thing to note is that this side of your diagram is a passive continental margin. This side is an active continental margin. You'll see that an active continental margin where the activities are very severe, you'll see that the slope and the shelf are much steeper as compared to the slope and the shelf on this side of your diagram as such. Okay, let us move ahead. Another view of these same features as such. Okay, you see the broad continental shelf moving into the say slope, and then you have the longer. Okay, that is why I've given you a multiple view into all these planes as such. Okay, you'll see that the continental rise is a longer feature as compared to the continental slope. Continental slope, sorry, I did mention it the other way. The continental slope is a bit steeper as compared to the continental rise. And then further deep, you're going to have the abyssal plain as well. Now, as far as some striking major features as far as respective oceans are concerned, let us start with the least ones. Okay. The Indian Ocean trenches include the Java Trench or the Sundar Trench. Okay. It is somewhere here, and as a consequence, you'll see the length of that trench is nearly 4,500 kilometers. The width is 80 kilometers. So it's a significantly dangerous trench, I would say. As compared to that, the Indian Ocean trenches, okay, are not that deep. Okay, you'll see this was for and length or lengthwise also. Okay, you'll see that the width may be same, but lengthwise Atlantic Ocean trenches are much less. And you'll see that one of the major trenches, as far as the Pacific Ocean trenches are concerned, many of them are long, but the longest of them, if you can see here, which though is not the deepest, okay, you have the longest trench, which is nearly 6,000 kilometers long. Okay, this is the Peruvian Chile trench. Okay, this is the location where you're going to have that Peru Chile trench. Okay, you'll see that the Pacific plate is going down here, and the American plate is moving the other way. Okay, so that is what we have to keep in mind here. Uh, then you have the next longest, I would say, the Aleutian Trench. Okay, this is the Aleutian Trench where you have it. And then you have the Tonga Trench. Tonga Trench is here. Okay, the Java Sunda Trench is here, by the way, okay, extending into this part as well. And as far as the Atlantic Ocean trenches are concerned, the South Sandwich Trench is here, and the Puerto Rico Trench is somewhere here. Okay, so these are some deepest parts of the surface of this particular planet. And another view of how it would look like. Okay, this is the boundary, let us say the coastal plain, or also called as the shoreline. And then you have a gradual drop, which is called as the continental shelf. A steeper one is called as the continental slope, and then the longer one in general is called as the continental rise. So 1 plus 2 plus 3 is actually called as the continental margin. All this makes up the continental margin. This indicates at the fact that possibly this could be where the, say, the extreme fall in sea line. Okay, it's not exactly possible, but you could say that these are those areas. And then you have these small mounds, which are called as sea mounds. You will find them on the continental rise as well as the abyssal plain, which is the lower portion of the submarine relief. And then you have these submarine canyons also. Okay, so that is one, another one. And yeah, we were speaking about various types of margins. Okay? You have active margins and you have passive margins as such. You'll see that you have, say, the whole Pacific Ocean is actually surrounded by what can be identified as active margins. You'll see that around New Zealand also you have an active margin. This whole part, which is full of islands here, this is active, known for a lot of volcanic activities. So are these. Here you have the Caribbean islands. Okay, these are the East Asian, you could say. Down here you have the Indonesian islands, and then you have Philippines, and so on and so forth. Okay, majority of the rest of the part is actually a passive margin here. Okay, I would like to remind you all of this part, which is this here. The continental shelf is very broad. Add to that the cold and the warm currents meet here. So these regions of Europe are known for major fishing grounds as well. Okay, this is the geological distribution of the ocean floors as such. Okay, various relief features, and of course you can clearly mark out the mid-Atlantic ridge, particularly for the Atlantic, partially for Indian Ocean, and then the other forms that you can see here. Another diagrammatic representation of how a cross section of any surface would look like. Okay? Here you would have the trenches as such, and here you have the sea mounts, and it is along this that possibly the splitting is taking place. Okay? So the fresh rocks are going to be nearer the trench, and the older rocks are going to be away from the ridge as such. Okay, the continental shelf, this part, the continental slope, this part. Okay, the same thing on this side. Okay, a bit more gentler, as we have said. The American side is gentler. Okay, we'll have the abyssal plains. This is the abyssal plain here. Okay, trenches, as already referred to, okay, and the ridges. One more picture of that in a different scale, I would say, and a position as such. Okay, the continental shelf, slope, canyon, continental rise, mid-oceanic ridge. This is the sea level, and then you have the abyssal plain, and the hills on the abyssal plain are called as abyssal hills. And those islands which peak out of the mean seawater level are called as island arcs also. And one more of this scale. So I've put up so many of these that if you have not understood it out of one, you should be in a position to understand it at least at some other ones also.
Sir, can you
Yeah,
tell again, please, what is abyssal plain?
the deepest part of the uh, ocean is called as the abyssal plain. Uh, See this part here, deeper. And let me see if I can bring up more of them. Okay, this part is abyssal plain, the deepest part, very deep. And yeah, here see the deepest part, the abyssal plain. And any more? This the deep ocean floor. What is labeled as deep ocean floor is nothing but the abyssal plain as well. Okay, so let us move ahead.
So then, what is the difference between ridges and this abyssal plain? Because ridges are more deeper, right?
Yeah, yeah. This is the ridge. This is the ridge. The V-shaped valley is the sorry. This is the trench. Okay, this is the trench. The inverted V is the ridge, and what you have in between them is going to be the abyssal plain. Just let me try to make it up in some of the diagram. If I'm able to, I will obviously. Yeah. See, this is the ridge. The ridge is taller as compared to the surrounding areas because it is, of course, spewing up a lot of volcanic activity. And then here you have the deeper trenches. The average between them, this section, is the abyssal plain. Getting it?
So, and what about trenches? Like, is it ridge and trenches are same?
What? What
Ridge
was your
and
question?
trench, ridge
No,
and trench is
no,
same,
no,
right?
no. They are not. They are not the same. Okay, you'll see a ridge is inverted V, and a trench is a proper V. I told you. I just showed you. Just let me once again point it out.
Okay.
Okay, this part deeper. The deepest is the trench. Okay, the deeper is the abyssal plain, and then here you have those ridges. Okay, so this is the ridge part. This is the trench part. Okay, the difference is they may look similar, but the difference is that the plate is going down here, and volcanic material is being pushed up from here.
Okay.
Okay, now that was the physical aspects of the ocean floor as such, and now let us come to the chemical aspects of the oceans as such. You would be surprised. Anybody remembers these diagrams that you are seeing on your screens now? Have you seen them anywhere earlier? Remember them? I fetched these from your school textbooks. So it's not that once you're done with your schools, what you learn in your schools is not that important. At times it comes back to you and you could understand it further as far as this at an advanced level is concerned. Um speaking about the depth and the temperature of the sea water, let us start with this. Okay, you'll see that you have these as temperatures, sorry, okay, temperature in Celsius. Okay, this is 20 degrees and then you have 0 degrees here. What is interesting to note is that the oceanic waters never go to 0 degrees. It's one thing that you have to understand. Saline waters particularly. And these curves, you'll see that in higher latitudes, high latitudes, temperatures are around 4 degrees. K is where we know to have them as to behave like what is called as the anomalous behavior of water is what this happens at 4 degrees temperature. This is the curve of the mid latitudes, you'll see. Okay. Near the surface, okay, the temperature is high, it's around 14 degrees. Then it starts falling slowly till around the first 200. This happens slowly because at around till this particular depth, the energy of the sun's rays, okay, the heating of the sun's rays takes place in these layers. So the fall in temperature is going to be less. Okay, and because of that, you'll see that the fall is gentle here, but once the sun loses its impact, the energy from the sun loses its impact on the water, say around by around 300 meters from the surface, you see that it starts dropping very rapidly, and you'll see that in the next, say 1200, 1300 meters as such, it drags it down from 10 degrees to nearly 4 degrees as such. As compared to that, in the equatorial or the tropical regions, again, because of the insolation being more, you'll see that the curve is very gentle, but beyond 700 meters, it joins the earlier curve. It falls very rapidly. And then beyond, let us say, 1700, 1800 meters, the temperature stabilizes at around 5 degrees centigrade. Sorry, 4 degrees centigrade as such. So this is what happens with the depth and temperature of the seawater. And having done that, okay, an interesting fact that we have to note here is about the Dead Sea. The sea itself gives an idea of the conditions there. The sea lying on the border of Israel and Jordan has a salinity of 332 parts per thousand. Okay, this is per thousand, not 100. Per thousand. The average salinity, however, of an ocean is 35 parts per thousand. Jordan is the only large river meeting the sea. And in fact, nowadays, what has happened is they have built a lot many dams across the river Jordan, which leaves a very less amount of fresh water to join the sea as such. Okay. Plus, add to that, low rainfall, low supply of fresh water, and high evaporation are the reasons of high salinity in the Dead Sea as such. There is no life here except some unicellular organisms. The fish coming from the river Jordan die as soon as they come here because of the high salinity. Saline pillars tend to develop in these areas as such, okay, where you'll have the fresh water and you have the saline water meeting. Okay, what happens is the salts will drop down and you'll have saline pillars as such. Some of them come out of the surface as well. The density of water, okay, is also very high because of the higher salinity. Therefore, one can never drown in this water. We can easily float when we go to this seawater. Another characteristic of Dead Sea is that the land here is below mean sea level. It is one of those places having the lowest elevations on the earth. In some areas, the altitude is as low as minus 400 meters. These are the salt pillars, you can say. Okay, so that's one chemical aspect. The second or the other chemical aspects, okay, you'll see that as far as the depths in meters are concerned, from mean sea level to around 4,500, we have already seen that the temperature will drop, okay, from around 20 degrees gradually first and then very steep. And you'll see that as far as temperature is concerned, it is inversely proportional to density. So while the temperature curve is this way, density curve is this way. Okay. Colder waters are going to be denser. Okay, so from here it starts getting cold. From here it starts getting dense. Okay, you will see that this curve is gentle. This curve again towards higher density is here, and then you have salinity per thousand as well. Okay, salinity goes with whom? Salinity goes with temperature. Okay, lower temperature, lesser salinity. Okay, so it's this way. This is how you compare these with each other. In fact, you'll see that these curves will change as far as various latitudes also are concerned, but we are not to go into that. That is a part of some studies that oceanographers in detail would do at some point of time. As we said, that it's all made up of salinity with different types of salts as such. If we take a sample of seawater, okay, you'll see that 96.5% of it is basically water. A small percent of it, okay, 3.5% or 35 grams is actually the salt. This salt is further divided into various other salts as such. Major salts of them, 80% of it is sodium and chloride, and that is why NaCl is the common salt that we use. Sodium, NaCl, 55 and 30, 85%. And then you have other small constituents as such. What are these constituents? These constituents include 8% of sulfates and magnesium as well. Okay, so go to see it, you'll see that 95% of these salts are chloride, sodium, sulfate, and magnesium. And then we have a very small percentage of calcium and potassium as well, 1% each, let us say. And then you have other minor constituents. These are the salts that make up a major part of the salinity as far as seawater is concerned. Okay, this is the surface density map as such. Okay, you'll see that in the tropical regions, the shades are lighter in color. Okay, so the density, sea surface density is lesser. And as you move towards the colder parts, the sea surface density increases as such. This is to do with a lot of rivers that bring in a lot of fresh water here as such. Okay, this is going to be the mouth of the Amazon. This is the Congo, Zaire. This is the La Platte River, if I'm not wrong. And then, of course, you have the Sundarban Delta. You don't have major rivers in the Arabian Sea, so this looks a bit tingy, bluish as such. But as you go towards the equator once again, okay, because you have a lot of rain around the equator, you'll see that the shade of the color is whitish as such. Okay, and you'll see that the tropical waters are the whitish, less dense, and otherwise as such. Okay, so that is as far as the sea surface density is concerned. This is an interesting aspect, the sea surface temperature. You'll see that it is seen to be shifting, okay, with reference to some dates that you see changing here. Okay, it is a thermal, say, scan, and then you have a timeline series of what is happening between 2012 and 2014 and how the red patch is shifting north and south. This, of course, is to do with the summer and winter of the respective hemispheres, that the warmer temperatures will move north during the summer of the northern hemisphere, and the colder bear and the warmer will further move south when you have the summer of the southern hemisphere as such. Okay, you see how it's moving north and south. And then this is the salinity GIF of the ocean waters as such. Okay, you'll see that the bluish tinge is where you're going to have very, large amounts of fresh water added into the sea. And the reason they shrink and increase is because of the fact that the rainy season. It coincides with the rainy season. More rains, more fresh water, more fresh water, more salinity. Less rains, less fresh water. Okay, you'll see that you have lesser rains around here, so it hardly changes here. But as I said, I told you all that the larger deltas of the Amazon, just see the distance to which the Amazon carries its freshwater impact. I think I told you all that it travels up to 200 kilometers from the mouth of the Amazon. Okay, huge distance to which it travels as well. This is once again a detailed, I would say, representation of what is happening as far as the ocean flow is concerned. Okay, this is a map which normally experts would use. Okay, it's not as simple as the earlier current diagram that we saw, but we can try one of them by enlarging them. Let us take this here as such. Okay, you'll see the South Atlantic current here, and you have the North Atlantic equatorial current here. And this is the counter current I was referring to earlier in the morning. Okay, traveling in between here. And this is the gyre that we spoke about, the circle in which it tends to move. This is the North Atlantic gyre. We're going to have one in the south as such. The Gulf Stream, as I said, after meeting the Labrador, will move ahead as the North Atlantic current, further as the Norwegian current, and then the North Cape current. Then it's going to take a turn around and it's going to get cold and come down here. The East Greenland current. Okay, and it moves here and comes down as the Labrador current. Okay, a very interesting arrangement. You will see the cold Canary current is here. Okay, the warm Gulf Stream current is here. It's also called as the Florida current in some places, the Atlantic current, and so on and so forth. Okay, just check the location of where we are supposed to be having the El Nino. It's here somewhere. Okay, normally it's like this that it moves. Okay, this is the counter current, which when shifts south will attack this area. Attack in the sense it will come in this particular area. Peru current being a cold current will sink and the El Nino will ride upon it. And that is going to be the El Nino year for the world. That's how this all happens as. Okay. We spoke about these gyres. Okay. You'll see that you have this gyre where it's 1, 2, 3, one in southern hemisphere, also in Indian Ocean, also as such as smaller ones here and here, and so on and so forth. We spoke about the cross-sectional view, and you'll see that this is how an interesting near the poles, particularly. You'll see this is Antarctica, and this is the eastern flow we spoke about, and then we spoke about these western flows. Okay, while all this is happening, okay, you'll see that the thickness of these flows is much differently as such. Okay, you'll see that the Arctic surface water will dip down here. Okay, and in the tropical regions, you have subtropical surface, you have subarctic surface waves here. Okay, the North Atlantic deep waters will try to rise in this particular way. This heavier water goes down in the form of gyrated circles. And then we come to some major features as far as the ocean surfaces are concerned, and what you see in front of you are nothing but waves lashing the coast as such. Okay, as far as waves are concerned, they are a direct movement or direct result of wind that is blowing, and that wind is going to cause stress on the surface, and you'll see that the surface starts, so water starts moving, like the energy gets transferred, and while it is being transferred, the energy is being transferred, the water levels will rise and fall, and it is going to be pushed towards the land. While the movement is circular here, these circular movements, okay, will try to get flattened as you come to shallow waters. Okay, this is deep water, and then from here you're going to have shallow water. This shallowness is going to hit the circulation here, and because of that, you'll see that the crests have started climbing to an extent that the waves start breaking here. Okay, so that is how waves are generated toward the coastal area as such. Okay, this is the surfing zone as it is called, where the waves break, and beyond that, the dry part is called as the beach as such. This is how actually the energy transmits itself. Okay, you see the wave is transmitting itself, the energy is transmitting itself from one point to the other. But you'll see that there is not much difference as far as this bird, which is floating on the water, is concerned. Okay. Okay, it's interesting to note that in deep water, waves propagate energy, they do not propagate mass. Okay, so energy is conducted, I would say, mechanical energy tends to be conducted, not the mass as such. Okay, this is a very common misconception that people tend to have. Okay, this is how a wave looks like. Okay, the topmost part crest, the bottommost part is trough. The movement takes place in a circular motion. It's called as an orbital path. As to how an individual water molecule will move, the number of wave crests passing a point in unit time is called as the frequency of the wave, and the time required for one wave crest point at A to reach point B, okay, this to this point, let us say. This is called as the wave period. A few connotations used as far as coastal geomorphology is concerned. As I said, this is how water molecules will oscillate in deep water, but as far as shallow water is concerned, what happens is as you approach the coastal areas, okay, the shallowness, okay, will break, or rather they will deform the circular motion into more elliptical orbits, elongated orbits, and this elongation will lead to breaking. So you'll see that somewhere here the breaker zone starts. This is called as the breaker zone, and say following the breaker zone you have the surf zone, and then you have the swash zone. Okay, normally swash zones is where we actually stand and enjoy this area as such. The more daring ones will go into the surfing zone, and the most bold will go into the breaker zones as such. Okay, these two are not advised for non-swimmers particularly. Even swimmers have to adopt to a lot of caution when they are actually in these areas. We can just stand here and enjoy the say the rise and the fall of the water which comes with the waves also as such. Okay. We have just said that deep water waves, the particles are moving in a circular motion. As the wave tends to push upward, you'll see that this is now getting longer along one axis. And then, as I said, this is the breaker zone, and this is going to be the surfer zone as such. Do we make energy out of this particular source of energy? Yes, definitely we do. And we are going to come to that as well. We are again a bit of short of time. I will just confirm when we will be going into the details. What I'll do is I'll actually stop here, and let me ask you all that, okay, by the way, please put in your, those who are attending and have not put in their names as a part of attendance, will please put in their names in the chat box. Okay. to let me know their attendance. Let me tell you that another lecture's material is still remaining. Do you want me to take a lecture next Thursday, or do you want me to take a lecture tomorrow itself? What would you suggest? And finish the portion. Another 50 minutes and we should be finishing a portion. What do you suggest?
So let's take it next Thursday.
That far? Sure.
Yes, sir.
What do others say? Thursday is no issue for me. We could surely do that. So if that is the case, then we will continue next Thursday. I'll just stop the recording because I'll have to upload this as well.